Welcome back to my lecture series again. And I think today I would like to present a new talk series that is about solar energy forecasting in Thailand. I will cover the concept and the modeling part that will involve a lot of technical details, how to develop a forecasting model in renewable energy applications. And we're going to present some case study results that my research team has been implemented so far for the past couple years. I am Jigamut Songsri from EE Department, Chulalongkorn University, and this lecture note that I'm going to use in slide, uh, go publication section and go to the technical talk section, and it's going to be the first one, solar energy forecasting in Thailand. From the overview, okay, this lecture series will contain maybe about 5 or 6 videos. The very first one, this one, I will cover the introduction, like the overall concept, uh, the problem statement, and its detail in order to develop renewable energy forecasting. And the next chapter, chapter 2, we explain about technical concept. How can we use the machine learning concept, statistical learning concept to apply and solve the forecasting problem. And chapter 3, we'll go over the detail. We see some examples of solar forecasting techniques. Examples of models are linear regression, neural network model, LSTM, neural profits, support vector machine, and the tree-based models. Okay, so once we have fundamental concepts in applying these tools, in chapter 4 we just capture how people in the research community have been developed these forecasting model based on the existing techniques. What they do is to develop submodels, many models, and try to connect the submodels into different configurations. And chapter 5 is more like a common provide you like a common guideline. Once you develop a model, how to evaluate the performance, what are standard protocols, is there anything that we have to be aware of when reporting the performance in the context of renewable energy forecasting. And chapter 6 will detail all the case study results we have involved in many research projects so far. Um, we have worked with the utilities, EGAT, or การไฟฟ้าฝ่ายผลิต PEA or การไฟฟ้านครหลวง MEA sorry, MEA is การไฟฟ้านครหลวง and PEA is การไฟฟ้าภูมิภาค and we also have the test site in our department. We have a solar rooftop on the top of the building. We have a lot of other equipments that we're gonna present in this lecture series. So how about we're gonna spend maybe around half an hour to give you about the introduction, about the problem statement, and and how to implement it until the end. Like I want us to see the overall picture, starting from collecting the data, developing the model offline, and once we get the model, how to implement it. Um, the motivation of this research problem is certainly because of the penetration of renewable energy in Thailand, and the electrical consumption grows every year, and but so in order to exploit and make use of renewable energy generations, we also need a strategy in energy management to manage all the power from different sources, where the renewable energy is one of them. And of course, the challenge is that for renewable energy, they are random, they are unpredictable. So here I have some examples of solar irradiance. So um, solar power is directly and is proportional to the solar irradiance. So that's why I give the graph of the irradiance to see on the different days. The orange line is from what we call a clear sky model. So this is like mathematical model that tells you how much irradiance you would get under the clear sky assumption. Like if there is no cloud at all, there is no particle, what is the maximum solar irradiance we could get? And of course, we get the blue line. It is from the measurement from the sensor. So you can see some variation on some day, there are highly fluctuation during the day. Okay, so this becomes a challenge on how to predict the amount of solar irradiance, which further inferred the amount of solar power you could harvest from the solar farm. Mhm. So in this context, let's like characterize what are the involved forecasted variables. So in this context, uh, the main variable that we would like to work with is certainly the solar power and the solar irradiance. Um, Also, wind power plays also another important role in renewable energy. But I mean, in our research project now, uh, we just involve mainly with these two guys. So that's why all of the lectures here will have example of mainly from the solar power. We also have a related question. So how to predict the electrical load in buildings, in region, in residential area. Because in the concept of energy, you have demand, which is electrical consumption from the user, from people like us, and also from the generation side, from the utilities. Um, they have to collect all the power, all the energy from different sources. Mhm. So uh, yeah, so the the typical relevant research question is to predict how much generation we could have and to predict how much consumption that could occur in the future. And because when we deal with energy, solar energy is harvested from natural sources, and certainly it would involve the weather variable like temperature, like or the humidity, wind speed, and all that. In the context of solar power forecasting, I think that we can uh, unify the ideas into two main approaches. The first one is what we call indirect approach. This one, we focus on developing a irradiance forecasting model. So whatever we input, we plug in here. The challenge is to first forecast the irradiance first. And because of the characteristic relationship or the relationship between irradiance and solar power, it is typically I'm going to show you by the data again later that the relationship between irradiance and the power are typically linear. Okay, this is so nice. I mean, you can characterize it from equivalent circuit of the solar cells, so we can observe this phenomenon. So that's why once we get the forecasted irradiance, you basically converse the values by using maybe a simple linear model to the forecasted power. Okay. And in order to develop this block, it's basically the concept of solar panel efficiency. Like how much radiation you could get. You just simply multiply by the factor of efficiency of the solar panel, and you get the forecasted power. This is the first approach. We call it indirect because we going to forecast I indirectly in order to get P. Of course, certainly the other approach would be the direct approach, okay, where we develop the model that release the forecasting output as the solar power directly. So in order to compare between the two approaches, we can maybe make some comments that if you pick indirect approach, um, the this approach could be transferred, could be scaled in other solar farms or other locations because these model basically just explain the weather dynamics. Remember that the irradiance variable it comes from the physical nature of the sun. All right. So if this model will represent whatever input that you could have here, and it can capture the irradiance in the future uh, correctly. If this model is good enough, you can transfer to another location and in any location in the country. But basically this model can be transferred. But in order to apply the whole thing with your new location, you can simply change this block because this block would depends on the size of solar farm or solar panel. If you have solar farm that is has bigger install capacity, like 100 megawatt, right, in size, or the other one would be 10 kilowatt, right? So of course, this block would have a bigger factor. This solar side will have a smaller factor. That's all. So that's an advantage of indirect approach, that you fine tune this model, right, using a lot of data from different geographical locations, and you can use it for any locations in of your interest. However, if you have developed a forecasting model based on the direct approach, because this value depends on, I mean, this is solar power that where the magnitude of this depends on your solar farm size, right? If you have developed this model for 100 megawatt solar plant, certainly you cannot immediately apply your model to the other solar farm that may have different capacity. You still need to work on how to tune or how to scale the output. But that depends on the description of your model as well, because typically the input of this model may be a function of historical forecasted power. Okay. In our research team, the approach that we have worked so far would be the first one, because we see the advantage of having the irradiance forecasting model. Um, in now where I'm going to give give a technical specification of how we determine or define forecasting problem. Um, Proper forecasting problem consists of um, consists of the description whether you're gonna perform a point forecast or probabilistic forecast. So a point forecast is of course to give a single value of solar power in the future. For example, you're going to tell that tomorrow at 7 a.m. your p hat is gonna be some value. So a point forecast is certainly something that maybe you can mark it on the green line, that I'm giving you a point of solar power at different times in the future. This is what we mean by point forecast. A point forecast doesn't certainly it doesn't mean that tomorrow at 7 a.m., if I predict that it's going to be, let's say 10 kilowatt, right? Certainly, the real or the actual value of solar power may not be 10 kilowatt, but you hope that your point forecast is going to be close to this value. For probabilistic forecast, on the other hand, give you additional information about point forecast. Instead of telling you only that tomorrow is going to be 10 kilowatt, it gives you the sense of how this value is going to vary, or how much the variation of this point value is. So one example of the probabilistic forecast is to provide an upper bound and lower bound, where it basically says that your forecasting value could be any value inside this interval. This is to provide what we call prediction interval in the yellow area. Okay. So that's the first one. You have to tell whether you're gonna develop point forecast or probabilistic forecast. Is your choice. Mhm. Secondly, you have to specify what would be your horizon of the forecast. We have some example of horizons in this picture. The first one is called day ahead. You can say, I'm going to provide a 1 day ahead forecast, 2 day ahead forecast, or 3 day ahead forecast. So the horizon is how far you look in the future, um, and you're going to predict those value. In this example, my blue line is the marker of the current time t. This is the time that I'm going to perform the forecasting values. So this is an example of uh 3 day horizon, because every time I perform a forecast, I look to 3 day in the future. Another example is hour ahead. Let's say my horizon is 6 hours. So it means that on any time t, during the day, what I'm going to provide you is that I'm going to provide you these value, or the pi. Okay. But the furthest I go is 6 hours. Okay. The last example is minute ahead. Of course, it means that your horizon would be shorter in order of minute. You could say that my horizon is 15 minutes. Okay. That's the second aspect, second bullet in your configuration. Third, the resolution of your forecast value. Okay. Let me give you an example that in this in this example of day ahead forecast, I say that my 3 day is the horizon, and I can say that my resolution is 30 minutes. It means that the resolution of these values is 30 minutes. So let's you take a break, you pause the video, let me and please help me calculate. If you're given a forecasting specification at 3 day horizon with the resolution of 30 minutes, I want you to calculate how many steps, how many forecast values you need to release every time you perform a forecasting. Pause the video and calculate. The answer would be the number of points that you need to release is, of course, 3 days, right? Each day has 24 hours, right? And in 1 hour, how many points? How many points in 1 hour? Now you look at the resolutions, which is 30 minutes. So in 1 hour, you have 2 points. So that's the number. That's you multiply these out. 3 times 24 times 2. Okay. And what's the number? What's the number? is 134 points. These are the points value of the forecast you're going to release every time you perform. Um, okay, the fourth bullet is the time step of forecast computing. This is I mean this configuration is relevant when you deploy the model, when you actually implement the model on the platform, when you infer the forecast value. How often would you execute your forecasting model? This one doesn't have to be the same as resolution of forecast, but you might see that people may set these two guys to be the same. Like if your model need to release the forecast value in the resolution of 30 minutes, people may pick that, oh, maybe I update the forecast value every 30 minutes, but it doesn't have to be that way. Mhm. For example, for day ahead forecast, people can set the model, people can choose that I'm going to perform a day ahead forecast just every day. So the time step of forecast computing would be 24 hours. Okay. Um, Sliding, non-sliding would be kind of a detail, like when you when you this is going to be something in detail. It basically means that first, if you release the forecast, for example, like these three values, okay, this is uh this is marked as I perform the model at the green line. But certainly when I move to the next step of computing the forecast, let's say my time marker is the green line, right? So I'm going to have another set of forecast values. Of course, you would see that if I pick any time here, you have the forecasted value from the red one and from the green one. I mean, let's see that okay, let me mark here. So let's just say this is someday in the future, August 17, let's say 11 a.m. All right. The forecast value of this time can be obtained from the red line, from the green line, which differs by the forecasting times. So the matter of sliding and non-sliding would be a matter of your choice, whether you're gonna update the model every time you get new forecasting values. People can choose can use for example, if you perform the model in a sliding mode, which means you will say that I always keep the new forecast, which means I'm going to keep the green one instead of using the red one. Okay. Um, so after explaining this configuration, you will see that different problem statement would directly imply the difficulty of your forecasting problems, easy or hard. And maybe let's think about this together. Between day ahead forecast and minute ahead forecast, I mean, if you develop the model and maybe you evaluate the model performance, which one would be a harder problem to achieve the same accuracy? Day ahead or minute ahead? Okay, pause the video, think about it. Um, so the answer would be, okay, the further you look in the future, it's certainly harder because there are more uncertainty, more variation, there are more unpredictable things in the future. It would be certainly like very uh, feasible to predict things in a shorter horizon. Okay. But when we look about the model performance and the details, there will be a lot of other aspects that impact on has an impact on the model performance. I will explain this in another video when we talk about the performance evaluation. Okay. So my last comment is that when you read research papers, or when you try to justify, compare, or benchmark different models, different works, it is important to take a look at the problem statement first. If two research paper do not solve the same problem statement, I don't think that they can be directly compared, right? You cannot say that this guy will beat up this guy, because certainly this one is typically easier. Okay. Mm. Um, I also would like to give some examples of how different problem statement can be used in application, because you may have one questions that, of course, certainly that you see that different configuration leads you to different problem statement, but how can we select this value? The question, the question can be answered just simply by following the common practice. When you develop something, it means that you're going to use that for some application. So you have to, so this specification is not something that you just make it up. It should be traced back from people, from application, how they're going to use these forecasting values. So I have some example here that for day ahead, 1 or 7 days, for power system operator, that they decide the generation planning unit commitment, where they have to commit about, for example, tomorrow they have to commit which generation should be ready, should be standby in order to generate the power sources to the system. Okay, and typically for day ahead, the inputs of the model would involve the weather forecast. In a shorter horizon in our head, um, this is in application of load following, economic dispatch. So once the generation unit is committed, you can in our head you can adjust the for power outputs of those generators, so that they can follow the demand that you can predict within this horizon as well. For minute ahead, okay, in a shorter horizon, the application would involve spinning reserve and demand response. Okay, so now I give a list of typical input variables in solar forecasting applications. It would involve weather variables, solar power generation from the measurement. Okay, these also from the measurements. But if the measurements are not available, for example, the weather variable, we also typically acquire the weather forecast from uh, what's so called the numerical weather prediction, or NWP model. So these are these are physical models, NWP, and there are many institutes all over the world, from NASA, from NCEP, ECMWF. You have open source. Uh, you have open source. Uh, like WRF. Okay, there are many organizations who provide these weather forecasts. Okay, so weather forecast value that run under your phone would be some value that acquired by some model subscription. Okay, one of these models. The last one is what we call synthesized input. This is something that provide a trend value of solar irradiance. For example, clear sky irradiance, that we will explain the model description shortly. So this is the value of irradiance under the clear sky. Okay, this is mathematical model that rely on some physics law. Um, People may use some moving average technique in order to predict the trend of solar irradiance. So whether it's just classical moving average or exponential moving average, that basically uh, this is essentially autoregressive model where by using the real value of solar irradiance as the input. Um, Now on this slide, I give you an example of how the model is performed. A problem is to give the forecast between 6 to 5:30 in the evening, 4-hour horizon, resolution of 30 minutes, and forecast at every 30 minutes. So in this example, this is at 6 a.m. At 6 a.m., I'm going to provide a forecast of 4-hour horizon. So 4-hour horizon would end at 10 a.m. And how many points do we have here? How many points? So it would be 4 hours, right? And each hour contain 2 points. So you release every time you perform the forecast, you release 8 points of forecasting values. And certainly this black one will be slided every 30 minutes because you forecast at every 30 minutes. Okay. So the red one is the forecasting values and the blue one is the actual. So you see that sometimes you predict very well, this follow the trend, right? This is off because the actual value has some fluctuation. Your forecast just follow the smooth trend. So this is not like this is quite a poor performance. Okay, in this example. Now, on this slide, this is an example of deterministic forecast or point forecast. You give an approximate of uh, the value of your variable. In this example is solar irradiance. On the other hand, the probabilistic forecast is to give you the statistical information, and there are many ways. This is quite a huge area. There are many frameworks, many approaches that lies within. Hmm, I can like broadly categorize into two concepts. The first framework go to the direction where uh, you train your probabilistic models directly using in the training process. This one is typically harder, and this is still an ongoing project, ongoing research. The other one is first you develop a point forecast model, deterministic model that you did here. But once you get the forecasting values, you can calculate the error. You can calculate the error as, for example, y hat minus y, right, the forecasting value. And and of course, your error sometimes is small, sometimes is large, right? And then you're trying to analyze those forecast errors statistically. Some example is to plot the histogram and try to fit the PDF probability density function using different techniques, whether it's a non-parametric technique like KDE or the one with that assume the distribution. For example, people may have used gamma distribution, beta distribution, Weibull distribution. Those example. Um, okay, now this is the first example of how to provide probabilistic forecast. Once you get the forecast, the analyze of the distribution of the forecast error, you can say that if I want to uh conclude about the interval that cover maybe zero point 0.9 probability, right? So you can get this as a lower bound and lower bound, and then you can report this as a prediction interval. This is my variation. This is um, my variation of the forecast could be that I know that correspond to the significant level of 0.9. Mhm. Okay. Um, if you wanna but there's a other approach of telling the uncertainty information or statistical information about the forecast as well. We have the concept of quantiles. Um, Let me remind you a little bit about the definition of quantile. If you have a variable y, the tau quantile of y, by using this notation, is the value is a value where your CDF, your probability of y less than this value equals tau. In short, if we have um if we have what if we have suppose this is CDF, right? This is the value of y, and this is the CDF of y, right? Given the probability tau, right? This value is called quantile of y. Mhm. Uh, the concept can also be explained uh, certainly also by the PDF app as well. But for the PDF, it means that if I if I give you the value of q of tau, right, which means I look at the area under the PDF and see which value that correspond to the area that gives me the area of tau here. So this is going to be the quantile of y, the tau quantile of y. Um, one simple fact about the quantile is that if I so this is example of quantile at 0.99, right? Because that corresponds to a higher value in the probability. Let me ask you, what about quantile at 0.01? Where is it? The quantile of the 0.01 quantile would somewhere around here, right? So the quantiles values are in increasing order as you increase the associated probability. Okay. Um. hmm, Uh. So that means when you have if you wanna explain about statistical information, you can say that, okay, this is my quantile 0.1, this is my quantile 0.2, my quantile zero point 0.8, my quantile 0.9. If you can get these like bunch of quantiles, but of course you understand, right? I mark quantile 0.1 here, it means that the area here is 0.1. I mark quantile like 0.2, it means that the area here is 0.2. Basically, if you can gather like the bunch of quantiles, is this the same thing as you get the discrete approximate of your CDF or PDF? And it's the same thing of telling the distribution of your forecast value. So a prediction interval can be derived. It is a byproduct of knowing the quantiles. So I can say if I pick point 95 quantile, okay, this is supposed to be 0.05, and if I pick the 0.05 quantile, so if I'm interested into this value, right, it means that the area between these two quantile take the area of 0.95 minus 0.05, which is 0.9. So if I extract the values of quantile, all right, um, let's say, uh, I think in this graph, oh sorry, in this graph it doesn't give example of quantile 0.95. Uh, in this graph it gives you different quantile, or let's say this is quantile of 0.9, and this is quantile of, in the graph, it's quantile of 0.2. If you know the two quantiles, you know that the area between these two values takes the probability of zero point 0.8. So you have a significance level of 0.8 to give you uh, the uncertainty information. With the probability of zero point 0.8, my forecast can lie within these two bounds. Okay, so this is a problem of developing the quantile estimate, and it is under the framework of probabilistic forecasting. Hmm. I also would like to make a note that these quantiles are actually conditional quantile estimates. These quantiles do not is not obtained from the variable y alone. Um, so the framework would be, you're gonna have some model setting that whenever you put the input x, and you're going to get the quantile of y at probability level of tau. But this is let me use the same notation. I use qy at tau, right? So it's q of variable y at tau, but it's gonna be a function of x. So that's why it is called conditional quantile. So it is a function of x. So it means that this point, right? This point is certainly come from some x. This point come from another value of x. So even though they have the level of probability as 0.9, like the same value, the values of quantile can be different. Mhm. When you get the prediction intervals, all right, this exam on this slide, I get the information, the prediction interval from the two quantiles. But there is also a framework of developing or training the model to release the prediction interval directly. Okay, so this example, yeah, is illustrated by the yellow bands. Okay, sometimes so I have on this graph I have both examples of point forecast, which is in the red line. I also have the actual value. You see that sometimes there are mismatch, right? There are a lot of mismatch here. And also the prediction interval in the yellow band. In this example, the prediction interval associated with some probability, it just gives you the what? It just gives you the area for which your forecast could lie in with some significant level. It doesn't tell you 100% that your forecast value will lie in that interval. So that's why you see that's why you could see that do I have this example? Um okay. I okay. In this example, it turns out to be that in this example, my forecast value lie within the prediction interval always. Okay, but I'm saying that in practice, or I mean, it doesn't have to be guaranteed as that always. But and when you develop a prediction interval, it's a prediction interval of your forecast value. But you also hope that this prediction interval should cover the actual value, right? So now we can see in this example that it could occur, right? And that tells you the model quality. It could occur as well that your actual value could lie outside the prediction interval. Okay. So this is an example of poor performance on some days. All right. So this is like, when you perform the model on the hard data samples. On the easy data samples, when the fluctuation of the weather is less, all right. So this is solar irradiance. I think this is the variable that we forecast in this slide is solar power. Sorry. So the solar power is very smooth. At noon, you get like a very high power. So in this case, you see that your forecast perform very well. It follow the trend, and you have the prediction interval that cover both the prediction and the actual value. Okay. Um, I think yeah, I'm gonna break the video. I think I give you in this video I just give you an overview of how to define a forecasting problem. So in the next video we're gonna tell you how to follow this journey. Like how do we starting from collecting the data, developing the model, and how to implement it. Okay.